In this video, I'm going to modify this program that you see in front of you, but I'm going to modify it without the source code. Look at the mistakes here. We check if argc is above 2 instead of saying above or equal to, and we always print the no arguments message even if arguments were provided. But let's say you don't have the source code. How do we fix this? Well, you fix this by disassembling the machine code of this program and modifying it. And that allows you to patch or modify programs without even having the source code. This is known as reverse engineering. Let's begin. So we can see if we run the test program, it says no arguments. We say ABC, we see no arguments. If we say a second argument, so there's two arguments, we see multiple arguments provided, and we also see no arguments. Okay, I've now opened up X32 Debug, which is a debugger that allows you to debug executable files in Windows without having the actual source code. Okay, you'll see all of this weird stuff, right? This is called assembly language. It is essentially human readable machine code. Now, the first thing we need to do is we need to find those strings inside of our C code that we wrote earlier. So to do that, we're going to right click here in X32 Debug. We're going to say search for all modules, string references. And now you can see multiple arguments provided, which is one of our messages, and you also see no arguments. Just click onto that. And now we can see the assembly language for our main function. Now what you see here is disassembled machine code. And this machine code is executed directly on the processor. For example, the push instruction you see here pushes something into memory on the stack. This instruction here moves the value in the ESP register into the EBP register. Now, all of these instructions mean something. Here, for example, we're reserving space on our stack by subtracting it by 10. Our compiler, for some reason, has put in a subroutine call to this function. That was not something we made, and it's something the compiler put in for whatever reason. What we care about is here. This here compares argc to 2. Now, argc is in the base pointer plus 8 in memory. Now, this makes sense because when a function call happens in C, we push arguments to the stack, and then when we call the subroutine, the return address also gets pushed to the stack. And the return address allows us to return after executing a function. Okay, so you can see this ret instruction down here. This will pop the return address from the stack and make the processor execute whatever that address is, essentially returning from the function. So at this point in time, the EBP register holds the address of the stack pointer when we entered this function. You can see here we move the stack pointer to the base pointer, right? After pushing the base pointer to the stack. So by doing +8, we essentially skip over this push of the base pointer, which is 4 bytes, because this is a 32-bit executable. And then the next 4 bytes after this push is the return address. And then finally, we have the argc value. So that is why we do EBP +8. So here we essentially compare argc to 2. And if it's lower than 2, then we jump over the instructions that output the multiple arguments message. However, if it's greater than 2, then this jump will never happen and it'll continue executing our instructions. And what then will happen is we'll push the address of multiple arguments onto the stack, okay? And then we call the puts function, which outputs it to the screen. So by modifying this assembly language, we can fix our bugs. So let's now head over to the memory map, and we're going to go to the data section. And this is the data section here. We're going to look in here for some space where we can write our new code. Now, this could corrupt executables if that data is being used, but because this is such a simple program, we should be okay. So we're going to right click on the address and press disassembly. And now we can see the assembly language for that data section where it's been disassembled. So now what we're going to do is we're going to take the assembly in here We're going to copy it. And we're going to put it here. We can see that that successfully says the multiple strings, the multiple arguments message provided here. You have to be careful when copying the binary directly because sometimes there's relative addressing. Then it can point to different areas, right? So then down here, just after the no operation, we're gonna do we're gonna copy the assembly for the puts function. We right click here, and then we're gonna go here. There you go. So we can see the function should now work as intended as before because we've essentially written the same code where it will print the multiple arguments provided message out. But now we want to actually jump over the no arguments message so it never gets outputted. And you might be wondering, why didn't I just insert the code here? Well, a lot of the offsets for assembly are pre-computed. So by making changes here, we can actually break the program. It's important we keep the alignment correct and also the offsets correct. Now here, we're going to make a jump instruction to the address 0x hexadecimal 401 5EC. And what that is the move 0 to the EX register instruction, which skips over this print of no arguments. You see? So now what will happen is we'll skip over it and just return 0. But obviously this code isn't getting run. So we need to, before we can do anything else, we need to actually change our jump instruction here so that it does jump to this new section of code that we've made. So we're going to modify it. We're going to right click on this JLE. And we're going to say assemble. We're going to say JLE 0x 403 0F8. We can see we're not able to keep the same size, so it will overwrite the next instruction, which is exactly what I was just talking about that could happen, which is why we've had to put it in the data section. We're going to press OK, and it says the assembly branch does not point to an executable memory region. That's because the data region is read-only, so we need to change it so that it's no longer just read-only. But it seemed to make the change anyway, so we're happy with that. So let's just change this puts to a no operation, because otherwise we're going to have a lot of problems when that is about to be executed. We're just going to right click, assemble, NOP. Okay, good. Okay, so with that completed, it does look like it's extended. But if you look at the addresses, they haven't changed, which means the offsets are the same, because some instructions use more bytes than others. So with the removal of that puts function, now if the if statement is below 2, we won't call that puts function causing the program to crash. We'll instead push the no arguments to the stack and then output that message and then return. However, we do want to change our jump instruction again because the address no longer looks correct. So we're going to right click assemble. We're going to change this to F0. Okay, there. Because F0, 403, 0F0, that is the instruction where we push the multiple arguments provided address to the stack. Okay. And obviously when we're done, we'll call 4015EC, which will jump here, and we'll put 0 in the EX register to return 0 from the main function. Okay, so we're almost done. Now what we need to do is make the data section writable, because you did see that warning that keeps popping up. So let's head over to the memory map. We're going to right click on the data section. We're going to say set page memory rights. We're going to say execute write copy. We're going to press set rights. There you go. And now it's writable. The final thing to do is to right click, press patches. We can see all these changes we've made. We're going to say patch file. We're just going to name it, let's call it test4.exe. And then in the command prompt, we're going to say test4. And we see multiple arguments provided, even though nothing's being provided, which means we made a mistake. But if we put multiple arguments, we see no arguments. So we've actually now got it the wrong way around, which was an easy mistake to make. So let's head back to the instruction we made, the JLE, and we want to change it, jump greater equal. Okay. So if it's 2 or above, then we'll call that. Okay. And that will fix both bugs because we put 2 bugs in the source code purposely. The first one is that we check if it's above 2 instead of above equal. That's a bug. And the second bug is that we didn't have an else statement. So now by changing that to JGE, we've now solved both of those bugs, because when I was assembling it just now, I changed it to JLE by accident, which means I was checking if it was 2 or below, which is why you saw in the program that it got reversed. So once again, now that we've done that, let's patch that again. We're going to say patches, patch file. With that now completed, we can do test 6. We see no arguments. If we put in ABC, we see multiple arguments provided. So we've now fixed the problem. And why does it say multiple arguments provided, even if we only put 1 argument? And that, well, that's because the argc also takes into account the file name, test6, as an argument as well. So it is actually correct. It's doing what we wanted. So yeah, you can see that we've patched the program without modifying the source code. And this is exactly how game hacking works, but on a much bigger scale because it's more complicated. But the underlying concepts are the same. You go through a disassembler like we've done here. You learn about the disassembly and the machine code, and you make modifications. And just like that, you can patch programs without even having the source code. So if you're really interested to learn more about this assembly language, the language of the machine, then take a look in the video description where I have a course for you that is discounted. And you can learn all about assembly language and master it. And then you will be able to do things like this too.